Good afternoon. My name is Dimitrios Gonidakis. I'm an architect with a master's in computational mechanics and solids, currently conducting my PhD research at the NTUA's Laboratory of Structural Analysis and Antiseismic Research. In architectural optimization, we traditionally handle daylighting and structural performance in isolated silos. Today, with the paper Radiosity-Driven Bidirectional Structural Optimization, I am presenting a framework that bridges this gap by forming a bi-objective optimization problem. When we are looking at the principles of structural optimization and daylight analysis, a natural question arises. Can structural topology optimization and daylight optimization be fused into a single framework? And how? The answer is yes. Despite sharing entirely different physics, they share a fundamental common desire, the removal of material. Structure removes mass to find load paths, while daylight removes mass to create apertures. If they both were seeking to generate voids within a shared design domain, a true fusion would be mathematically viable. But before we optimize, we must state how we calculate light. To model our daylight field, we use a simplified form of the rendering equation, the radiosity method. The total leaving illuminance Bi from surface path I is the sum of the direction emission Ei and the reflected light from all surrounding paths J, weighted by their Q factors F, J to I, and reflectivity ρ. In matrix form, this simplifies to our governing system KB equals C. This system allows us to compute a fast, deterministic, and differentiable daylight distribution inside the room. To optimize this, we define a target illuminance for the room. We state the problem using a generalized least square formulation, calculating the deviation of the structural lighting form from our target. Crucially, we normalize this error by the mean illuminance to stabilize the gradients across vastly different sky conditions. So, how do we design the facade based on this error? This is how inverse radiosity topology optimization, or IRTO, works. First, we compute the forward light distribution B. Next, we evaluate the normalized error on the floor. To find how its elements density influence this error, we utilize the adjoint method, solving the system transpose K lambda equals B lambda. This efficient backward propagation outputs our daylight sensitivity numbers, which indicate whether adding or removing materials at each element improve our daylighting performance. Here is where the fusion happens. This unified flowchart details our coupled framework. Radiosity-driven bidirectional structural optimization, or RDBSO. We initialize the design grid and split the analysis into two parallel physics paths over a single search domain. The daylight domain solves for inverse radiosity and computes global daylight sensitivity. Concurrently, the structural domain runs a finite element solver, KU equals F, and evaluates local strain energies. Both sets of sensitivities are then sent to the coupling node for integration. When merging these fields, we must address their spatial characteristics. Daylight sensitivities are globally coupled. One pixel opening changes the illumination across the entire room. On the other hand, structural sensitivities are highly local, driven by an element's individual strain energy. To resolve this, we dynamically normalize both domains by their standard deviation and merge them using weighted factors. where W equals 1 represents pure structural compliance and W equals 0 represents pure daylight. To validate our couple RDBSO framework, we applied it to a real-world architectural context. A south-facing facade located in Athens, Greece. Athens presents a highly demanding Mediterranean solar envelope characterized by intense direct daylighting and severe midday glare. Our structural boundaries are designed to align with standard BESO benchmark. For daylighting analysis, we evaluate the facade under the CI Sky 7 model under local solar data for a winter morning at 9 o'clock and winter midday at 12 o'clock. The main deviation from the standard benchmark was our volume target. While a 30% volume fraction is the most common in structural optimization, we proceeded with a 50% target. This was done to approach the Greek Energy Code (KINAC) and local architectural committee guidelines, which typically propose a facade void percentage between 30 to 60%. By running a 30 by 30 grid under a strict 50% volume fraction, we test whether the algorithm can naturally satisfy both structural constraints and architectural daylight requirements without manual intervention. Here are the Pareto fronts under the standard morning sky at 9 o'clock for both boundary conditions. The graphs display our normalized daylight error J on the vertical axis against structural compliance C on the horizontal axis. Under standard conditions, our framework works exceptionally well. As we shift the weight factor W from 1 to 0.2, the facade topology adapts seamlessly, and we find highly stable, structurally sound geometries that dramatically reduce lighting error. On the other hand, at the extremes, we hit a fundamental limit. Under extreme midday luminance, the graph inverts. As we give more weight to daylight, the performance actually drops. Why? I call this the target volume conflict. To block intense glare, the daylight objective demands a heavily closed facade, but the structural solver is a priori forced to reach a 50% void target. These two physics enter direct opposition. The systems need to remove material for structural volume classes with daylight needs to retain material for shading, causing topological breakdown. In closing, we have proven that merging structural topology optimization and daylight optimization using weighted factors is mathematically viable under low illuminance conditions. Nevertheless, this method reaches a fundamental limit when illuminance levels are high. To address this limitation, our future work will focus on transitioning our update scheme to the method of moving asymptotes to handle nonlinear gradients more robustly, developing a dynamic volume target that scales based on real-time daylight requirements, and exploring varied facade orientation scale models. At this point, I would like to acknowledge the support of the Adapt4C project funded by the Marie Sklodowska-Curie Actions Horizon program. Finally, you can scan this QR code to access our full references. Thank you so much for your time, and I'm open to your questions.